Go.
Hi, how are you? So in this video clip, the primary purpose of this video clip is to show you or illustrate some of the things that we're learning in class about obtaining thermodynamic functions of systems in terms of partition functions of the system, right? So one of the things that we learn in class is an expression to obtain the energy of the system, internal energy of the system, in terms of the partition function of the system. So let me actually put it here. If you recall that it was given as nkt squared dln q dt at constant v. That's one of the things that we learned in class, and in a different video we actually derived this expression already for a system of distinguishable particles, right? So the goal in this video is to illustrate the use of this particular expression in a particular real system. The real system is going to be solids. We want to determine the internal energy of solids. Now, these solids will be represented by Einstein model. There are many other ways to represent it, but we are using a particular representation of solids, the one given by Einstein. In class, we will discuss the assumptions of this model and the limitations of these assumptions. So whatever results we get from here will be close to reality, but there will be some deviations from reality, from real solids. And in class, we will have the opportunity to discuss, the assumptions made by Einstein in his modeling of solids. For now, we're just going to talk about the mathematics associated with the model and how we can use that mathematics to get an expression for Q. And knowing Q, then we should be able to get an expression for the energy of the solid. In the end, we want to get at this particular result where it says that the energy is equal to 3/2 R, the ideal gas constant, 3/2 R theta, and theta will be defined later. It's called the Einstein temperature of the solid, plus 3R theta over E theta over T minus 1. Since 3/2 R theta is the result in the limit of T, the temperature going to 0 Kelvin, then is known, is first a constant, and second, we can represent it with that symbol E sub 0. So the energy at 0 Kelvin. So this is another way to express it. Okay? So let's see how we get here or here based on this. So things that we need, well, we need Q. We need an expression for Q. Things that can help us get there is an understanding of this system, the solids, as a system of harmonic oscillators. So you have a solid, suppose this is an atomic solid, so they have atoms all over the place, and then Einstein assumed that these atoms are fixed in position, right? In three-dimensional space they are fixed, but that they vibrate. There is a vibrational degree of freedom. And they vibrate all at the same frequency, right? So all atoms vibrate at the same frequency, and let's use the symbol nu for frequency, right? In 3 mutually orthogonal directions, right? With no particular direction favored. So that is, we have isotropic oscillators. Right, so The atoms are vibrating in mutually orthogonal directions, X, Y, and Z, if you want to call them, and they all vibrate at the same frequency, and because no particular direction is favored, then we say that these oscillators are isotropic. To obtain an energy expression for the vibrational energy state of the solids, of the atoms in the solid, we need to assume a model for it. So we think of this as being harmonic oscillators. So harmonic oscillators, right? And why do we want to do that, or why Einstein wanted to do that? But simply because that is, from quantum mechanics, we know what the energy expression is for harmonic oscillators, right? So we have all the elements in this model needed to come up with an expression for Q, and then from there we should be able to get the energy, internal energy of the solid based on that model. So some of the assumptions made, again, all atoms are fixed in space, but they vibrate in three mutually orthogonal directions with no particular direction being favored, so all of them are isotropic oscillators. So that means one single atom can be thought of as three oscillators, if you wish. And also these oscillators are harmonic oscillators, and that the frequency of vibration is related to the energy of the oscillators. So let's see how that really unfolds. Okay. Again, we're going to talk more about the assumptions of Einstein's model in class. Okay. So one is that the energies of the vibrational of the atoms, right, oscillating about their equilibrium position in the solid is given by this expression here. Okay? So V, right, corresponds to the vibrational quantum number. So V is equal to 0, 1, 2, etc. So now this is coming from quantum mechanics. From quantum mechanics, as you should have learned in your quantum mechanics class, the energy levels for the vibrational energy levels can be obtained for harmonic oscillators, and this is the result, right? And V is the vibrational quantum number, and the allowed numbers are 0, 1, and so on, right? So with this, there are many things that we can do. But first, the meaning. So this is the quantum number. So even at 0 Kelvin, right, or for V equals 0, right, the lowest energy is going to be half h nu, right? So even at 0 Kelvin, atoms are vibrating. They have vibrational energy. Nu is the frequency of the oscillation, right? That's what Einstein said for all atoms in the solid is going to be identical, right? Now, what can we do with it? Well, remember, Q, the partition function, the thing that we need to obtain this expression, is equal to E to minus E. In this case, we use V instead of I to say that these are the vibrational quantum states over KT, right? And it's the summation over the vibrational quantum numbers. Please note that I'm not using the degeneracy here. That's another assumption. All the modes are non-degenerate, right? So just this is what we need. Okay. So this, if we expand it, right, in a less abbreviated form, this is going to look like what? It's going to be E minus 1/2 h nu over kt when nu equals 0 plus E minus 3/2 h nu over kt plus, and keeps going. It's a series. Right? An infinite summation. For simplicity, right, we can set theta equal to h nu over k. Right? Remember, this nu is not, this is v, this is nu. Right? This is the vibrational frequency. H nu over k, what are the units for h nu over k? But if you go back here, h nu over k has to have the opposite units of this guy, so that the entire argument for the exponential term here, or for e, is unitless. So h nu over k has units of temperature, right? And that's why this is called the Einstein temperature, right? In the solid. So, and this now can be expressed as E minus theta over 2 t plus E minus 3/2 theta over t plus E minus 5/2 theta over t plus so on. This can be simplified by taking E minus t over 2t as a common factor of the rest. So this is going to be 1 plus E minus theta over t plus E minus 2 theta over t plus so on. Right? Please verify. This times this give me this. This times this give me this. This times this will give me this, and so on. So this is a way to represent QV. Well, it turns out that this part, the parenthesis, is a series or has an exact value. That series has an exact value, and the formula for it is 1 minus E minus theta over t to minus 1. This is how much we have advanced in our goal to getting here. Right? So I'm going to erase this and we can continue. We're almost done. But again, we needed a model capable of providing an expression for the vibrational energies of the atoms or the oscillators in the solid, from which we can obtain Q, the partition function, right? And now we are ready to carry out this derivative here, right? So that we arrive at our final expression. Okay, so let me do that in the next few minutes. Okay, so we need to since we need ln Q, the natural log of Q, let me get that from here already. So this is going to be equal to minus theta over 2t minus the natural log of 1 minus E minus theta over t, right? Or I will explain a few things. Ln, this is the product, right, of this term and this term. The natural log of the product is equal to the sum of the logs. So I have this term, the natural log of e to minus theta over 2t is just minus theta over 2t. That's what I have here. Plus, right? Plus. So let me just put the plus first. Plus the natural log of this whole thing. So I have to put back this negative 1. But as you can see, the exponent in the argument for log can be used as a coefficient for the natural log. So this negative 1, I can put it actually here. Right? So now I have an expression for the natural log of Q that I can use to obtain the internal energy. Right? Think about it. Try to anticipate what is it that I'm going to write here. Okay. Well, you guessed it. The ln Q dt constant V. Well, first this term here. This is going to be over 2t squared. Right? It's the natural log of this, but you have 1 over t. If you remember that from calculus, then this is going to give you the negative sign, but you have a negative sign here already. Negative times negative give you the plus. And then theta over 2t, the internal derivative here is going to be, again, given as theta over 2t squared. This is the derivative with respect to t for this term. Now we have to move to this other term. Right? So what's the derivative here? Maybe at this point, I'd like to recall, to help you recall that d ln fx dx, we have seen this several times already in previous videos, right? Is 1 over fx dfx dx, right? So we apply this to this, where this is now our function of t instead of x, but this is like calculus. From here, you should be able to get, right, 1 over 1 minus e minus theta over t, right? This is 1 over fx, and then times, remember I have this negative here, so let's put it back there. So I have this 1 over fx, and then the derivative of this function with respect to temperature, which is nothing more than theta over t squared e minus theta over t. But this has a negative sign here, right? Because minus times minus give you a plus, but then you have to do minus 1 over t squared, so that gives you the minus back. Now, minus times minus is a plus. So you can actually, from a stepwise process, or you can see it in advance, and just put the plus right there, right away. Okay? So this is what we have so far. Remember, we tried to get here. And this is what we have so far. So what is it that is needed? Okay? So we have this part, just multiply by nk. So energy then is equal to, all I have to do is multiply by nk. Let's consider an Avogadro number of particles. So n equal n sub a. So let n be equal to na. And Na means Avogadro number of particles, equal 3 Na oscillators. We're almost done. 2 more minutes, we'll be done, right? But it is important that we understand the meaning of the terms used in this equation. All that is left from this point is to multiply by nkt squared, right? That's all that is left, right? However, we need to understand what n is, what's the context of n for the solids. The solids is being described as atoms. Each atom is understood as the equivalent of 3 oscillators, right? So instead of saying n, you should say 3n, right? Because per particle there are 3 oscillators. And this is, after all, a description of oscillators. And if we use an Avogadro number of particles, then note that Na times K is equal to R, gas constant. That's from previous background. Avogadro's number of particles times Boltzmann constant equal R. Okay, now things start making sense, because nkt squared, the t squared here and the t squared here are in opposite sides. One is a numerator, the other is a denominator. Therefore, you will have nk theta, but remember, instead of nk, we're going to have 3 nak. So that means 3r, right? 3r theta over 2. So far, that seems consistent with this part. Right? Remember when we went to get there, well, we already have the first term. Very good. So we just move to the next one. Again, you have t squared in the denominator, you will have a t squared in the numerator, so it's gone. And then you have 3r, so it's going to be plus 3r, and then the theta is there, e to minus theta over t over 1 minus e to minus theta over t. Almost there, very close to it. What do you guys think is needed? Well, it's pretty much, we are done, but how do we make it look like exactly this one? The first term is identical, so nothing we need to do there. This one seems to have e to theta over t as opposed to e to minus theta over t. So what seems to be happening here? Well, let me focus on this part. E minus theta over t divided by 1 minus theta over t. Right? Let's focus on that component. What happens if I multiply and divide by the same quantity in a fraction? Well, the fraction is not going to be altered. If I multiply the numerator and the denominator by the same quantity, the fraction remains the same. So let me multiply by e theta over t above e theta over t as a denominator. What happened to it? Well, the result is this part on the numerator becomes a 1, and the denominator becomes e theta over t minus minus 1. And that, my friends, is this part of, if you have 1 here, times 1, so this part can now be understood because of this particular trick that is used to express the energy in a more convenient way. Okay, this concludes our derivation. We will talk about this more in class and have the opportunity to discuss the assumptions of the model and look at the limitations as t goes to infinity and as t goes to 0. We will talk about it, and then ways to perhaps address the limitations of the model using, or freeing some of those limitations that are part of the Einstein model. Okay, thank you very much. See you in class.